ingrained. So what we're going to start off with would be the example that I said we were going to start with, which would be, we're going to take a look at the carbonate ion. You should all know what the carbonate ion looks like. How do you know that? It was one of the things I told you to memorize. CO3 minus 2. Okay? How do we start Lewis structures? Total or valence electrons. Okay? Really, at this point, that should be an immediate response. There's no question. It's, oh, the first thing I need to do is total the valence electrons. So how do we start? Start with carbon. Carbon has how many valence electrons? 4 valence electrons for carbon. Okay? You have to remember, you do not count the core electrons. How many electrons does oxygen bring in? 6. How many oxygens are there? 3. So we'd have to multiply that by 3 or add 6 twice more. Last thing that we've got to do,
take away 2.
We have to account for the charge, and this is where we've got to be careful. The charge is what? Negative. How do we get a negative charge? We have to have more electrons. To get more electrons, mathematically, we need to add electrons. How many electrons do we need to add to get a negative 2? 2. So we've got our carbon, our oxygen, that's the wrong symbol for that, our oxygen and our charge, which gives us a total of, oh yeah, it is, 24 electrons. Where's the next part? Dividing by 2. It's not something that I'm going to say is wrong per se. It still will get you the correct answer, but it's what the textbook has suggested you do. I feel that that is an awful idea. There's enough mathematics already in chemistry. We don't need to add more mathematics pointlessly. Division by 2 is just that. So according to my rules, what would we do?
Find your least common.
We need to find our center atom. Which is our center atom? How do we know it's carbon? Least electronegative within that set. We can then scatter our oxygen atoms around it. Where do we scatter them around?
Equidistant.
Okay. There's 2 arguments. We could go equidistant, which is what I would do. Ultimately, the reason you would know to go equidistant, you already knew the answer. Okay. If you don't know the answer, and we'll discuss why that's the case in a little bit here, we should put it around the sides. Everything that we've seen so far, we've got 4 possible locations we can put things. Why 4? What did Lewis structures start with? A cube. We simplified the cube down to a square. How many sides are there to a square? 4. That's why we arranged them on the 4 sides. Okay? Now what do we do? We'll now put our electrons into the structure. Again, this is a difference between me and the textbook. I believe the textbook says to put them around the center atom. I think that's the wrong way to do it. You should put the electrons where? On the most electronegative elements. Typically, it's the outside. Why? Because we put the least in the center. Okay? So it's usually going to be to the outside. It is not always the case. The reason why the textbook has you divide your 24 by 2 is that now when you put your electrons in, you can either count the electrons and get to 24, or you could count the pairs of electrons. Okay? I would argue adding the whole extra term of pairs and division by 2 is just more complicated than necessary, and I'm pretty sure that if I can count up to 24, everybody else can just as easily. Okay? So it's not a necessary step, it just convolutes things. So we can now start putting our electrons into the structure. We put them around oxygen until when? What's full? 8 electrons. Why 8? Our octet rule. Why do we have an octet rule? Make it happy. I can kind of agree with that. What makes it happy? What does oxygen look like if it has 8 electrons around it? Looks like the noble gas. Okay, there's where our octet rule is coming from. How many electrons have we put into the structure? 8 around each atom, or 8 around our oxygens. We have 3 oxygens, 3 times 8, 24. Can we put any more electrons into the structure? No, why not? The most we could put in was 24. That's why we counted our valence shell. Okay? Now that we've got our electrons accounted for, we can go through and start to simplify our drawing. Okay? Where I would simplify is anywhere I have 2 electrons between atoms, I can turn it into a line bridging those atoms. What does that line represent? So a couple good answers there. I heard the answer that I would expect out of organic chemistry. It's a pair of electrons, 2 electrons. The answer out of this class, which was the rest of the class, it's a bond. Okay. Now is when I would go through and evaluate octets. Okay, so we go through for each and every atom, check to verify that it has its octet satisfied. The octet is not always 8, okay, but it most commonly is. Do our oxygens have octets? Yes. Does our carbon? How many electrons are around the carbon? Why do you say 6? I don't see any electrons on it. The bond is shared between the atoms, which means we can count those 2 electrons for each atom. Okay? So our carbon has 6 electrons around it. That's not its octet. It needs to get 8. How do we get 8 electrons around it? We need to share electrons from one of the nearby atoms. We've got 3 nearby atoms. Are any of them different from any of the others? No, which means which pair of electrons do we move in? Any one of them. Okay, so let's go ahead and pick, say, this oxygen pair. So this would be your organic chemistry version of it. We would take those electrons and move them in between the oxygen and the carbon. So if we now erase that and now said the electrons were there, what do we have? 2 more electrons between atoms. That represents a line. And we now have a double bond. Okay? And, which was the more important aspect, the octet. The octet is now satisfied on both the carbon and the oxygen. Okay? The oxygen did not lose those electrons because it's now sharing them. Okay? Did we have to pick that oxygen? No. We could have picked the oxygen up top. And we could have picked the oxygen to the left. Okay? So we would then draw those possible structures out and say, what's the issue with these? Can we tell a difference between any of these? Kinda, sorta. Your answer is fair to say no as far as energy goes. And this is where resonance can be a bit tedious. This is just as much as if we had kind of just rotated the structure. But when we're looking at resonance, you cannot rotate the structure. Which means each of these structures, or each of these oxygens, equally contributes a pair of electrons to the carbon. Okay, why does that become obnoxious? Well, if we draw, or we're asked to draw the Lewis structure for the carbonate ion, we have to draw all 3. Because only one of them, any one of those 3, represents one possible valid Lewis structure. We need to account for the Lewis structure, which means all 3. Okay? It's a bit obnoxious, but that's what resonance does for you. You have to account for those 3. Okay? Questions about that? Yes?
I saw a diagram of this where the bond shared between the oxygens and the carbon was connected by a solid line and a dash for possibles for each of the electrons to cover all 3 possibilities.
Sorry, I want to make that look a little bit neater. We do have this option as well. Okay. The reason why I would avoid this option largely comes from organic chemistry. Yes, it simplifies it, but then if you want to know something about the chemistry of that molecule, which oxygen has more electrons than the other oxygen? Okay, in that drawing, they all have the same. Have we accounted for our entire octet in that upper right-hand corner, the black one there? Okay. Officially, yeah. That's what those dotted lines showed. Is it something that was easy to see that we'd done? No. Okay? What we have in that upper right-hand corner is something known as a hybrid structure. Okay? Very, very rarely used because we've hidden a lot of the chemistry of that molecule, and we've lost a lot of extra information that we get out of drawing one of the Lewis structures, okay, a single Lewis structure. Does it accurately reflect it? Yes. And really, it's just someone getting lazy and saying, I don't want to draw it all out. Yeah?
So you want all the diagrams of each one?
Depends on the question asked. If the question asked was, provide the Lewis structure for carbonate, you would have to provide all three. If the question was, provide one of the Lewis structures for carbonate, you can pick any one of them. Okay? So it really depends on the question. Okay? It is a difficult concept. It's a concept that you will continue to see throughout your chemistry career because it's something that contributes to a lot of reactivity and stability. Okay? So you will continue to get practice with it throughout probably this semester and then other semesters as well. Okay? Both organic and 151. Last thing that we have to do before we actually say this problem is done, we need to specify that the molecule was charged, -2.
Do you circle the -2?
Good question.
Well, I mean, I know.
Which was going to be my kind of a jerk of a response. I always circle the charge, or try to always circle the charge. Why would I circle it?
Make it more visible.
What I'm trying to do is accent it and draw it away from it being a mathematical situation or a mathematical calculation. I'm saying the charge is -2. It allows me to see that that is separated out as a charge and not a mathematical operation. So you are not required to circle it. You're also not required to write it out as -2. You could also write it as 2-. I don't know why they do that. I think that notation is confusing. So I do the -2. Okay? Both notations are valid. Does that answer your question well enough?
Yeah.
Okay. The next question is, why did I draw that goofy looking 7? It's not a 7. It's my bracket. Okay. It's implied that the rest of that is now a bracket all the way out on both sides. Okay. Up to you. It is a very, very lazy bracket. Okay. You are more than welcome to use that notation. I'll understand what it means. Okay. Questions about your Lewis structures? Resonance. Okay. We will keep coming back to this every so often. Lewis structures. Okay. Lewis had a good job as far as organizing where the electrons went in an individual molecule. And that was kind of cool. Okay. We could see the bonding, we could see the arrangement. He could actually start to predict things about how different atoms would interact with each other. Unfortunately, Lewis's theory did a pretty awful job at explaining where those electrons went in a 3-dimensional space. You can only really do it for a 2-dimensional space. And what do we mean? If we take a look at the Lewis structure for CH4, I'm pretty sure we got this far last week. In theory, you should eventually get this fast as drawing Lewis structures. Okay, and we look at that, we want equal distances between each of those hydrogen atoms. Because each of those hydrogen atoms has the same nucleus. Each of them are going to repel away from each other as equally as possible. Same thing with the bonds in there as well. Those electrons want to get as far away from each other as possible. And we looked at methane, at least on the surface, we say, oh, they're all 90 degrees away from each other, except for the outer two. Those are now 180 degrees away from each other in our drawing. So we don't accurately reflect the 3-dimensional structure. Okay? So that's where valence shell electron pair repulsion theory came into play. Okay? So what they effectively did is took Lewis's theory and looked at the electrons in those bonds and said those electrons need to get as far away as they can. And somebody who's really good at 3-dimensional space could see that to arrange 4 groups around a center atom generates a tetrahedral shape. Okay? And somebody probably even better than them could go through and see how that shape would change if you had differing groups of electrons. Okay? Be it 3, 2, 5 sets of electrons, or 6. Okay? So when they initially approached this, they went through and came up with your electron geometries. So in that case, what we've assumed is that all of the groups of electrons around that central atom are the same. There is no difference between them. Okay? That can be taken a step further into something known as molecular geometry. Why would we see a difference between those? What does the H represent? What does the H in CH4 represent? What does the C represent? Carbon. What does the line represent? So this is the exact issue. When I say hydrogen, or H, everybody tells me hydrogen. When I say C, everybody tells me carbon. When I say line, I heard bond and I heard electrons. Why is that an issue? It's an issue because when we look at a molecule, we don't see electrons. We see bonds, we see other things. And yes, they're all similar, but we don't see the bonds. We see the atoms. So looking at an electron geometry, while it may make perfect sense when we look at the electrons, when the average person looks at a molecule, they don't see the electrons. What they see are the atoms. So we have to come up with a new geometry that will be based off of the electron geometry. That is our molecular geometry. Okay? So we're going to have to subcategorize how these different things and shapes can align and arrange with respect to each other. Okay? So with our electron geometry, we can start with one group of electrons and we can push all the way up to 6. Okay? The 5th and 6th you're not responsible for. They're included on here because you would be responsible for them in 151. Okay? So I want you to be aware that you can get more than 4 groups of electrons. Okay? So what we've got is some representative molecules and the shape that would be generated from that. And it's based on the electron geometry. Okay? All of our shapes, be it electron geometry or molecular geometry, are going to be based on a center atom, okay? Which is going to make things a bit difficult when we look at HF. If we drew out the Lewis structure for HF, okay, I'm going to attempt to go through all of my steps as quickly as possible. We start with our fluoride, put our electrons around, erase, and bond. There's HF. Okay. What's our center atom? It really isn't a center atom. We could say the center of the molecule is the bond. Okay, so when we're going to try and look at electron geometry or electron groups or any of the shapes, we need to pick a center atom. Which do you think is the center atom I was referring to when making this slide? Okay, so let's look at our possible options. We'll call hydrogen one option, and we'll call fluorine, which I'll just leave in red, as the other option. How many electron groups are around the hydrogen? There's one group of electrons. Our group is your pair of electrons. Okay, sort of. So hydrogen has one group of electrons around it. How about the fluorine? Still has that bond, but then we have a pair there, and a pair there. How many groups of electrons are around the fluorine? We get 4 groups of electrons around our fluorine. So as far as this problem or my organization of this slide went, I should have picked a better molecule. Okay, what was our center atom? Had to be hydrogen for the argument of this problem. Okay? So what we're deciding for one group of electrons is our hydrogen is pretty much going to be your standard case for one group of electrons. Okay? The geometry that comes out of that, well, if there's only one group of electrons, we're connecting 2 atoms to each other. What's the only possible shape we could get? Linear. There is no other option. Even if we moved my fists around, it's now just linear up versus linear sideways. Okay? Or linear diagonal. It's still a straight line. Okay? What happens when we move to magnesium chloride? A little bit of a trickier structure. Any of those dots aren't showing up, are they? Not really. Okay. So we could go through with our magnesium chloride, all sorts of fun. Erase, bond, bond. What's our center atom here? Why do you say magnesium and not chlorine? This one very clearly has a center atom. It is the center of this molecule. Okay? How many groups of electrons are around the magnesium? We go to our sides. We have one bond there, 2 groups. 2 groups of electrons. What's the geometry that we're going to get out of that? So now we've got 2 things, my fists, trying to get as far away from each other as possible. As far away as possible puts them into an exact straight line. So again, we have a linear shape. Okay? And since that's now getting awfully crowded in the middle there, let's take a look at one more example on this, just because this morning had a big question on this.
Magnesium didn't have an octet.
Which is actually going to get to what this next one was too. So let me redraw the magnesium. Does our magnesium chloride, do we need an octet on the magnesium? Where is magnesium? Second column. What's the most electrons that we can get on our magnesium? Just our 2 electrons. There's magnesium's octet. Okay? We're only looking at those 2 possibilities. Okay? It is a little bit weird with it because we end up putting 4 electrons around the magnesium, but that is its maximum octet. Okay? Magnesium will not exceed 2 bonds. Okay? What happens when we move to the boron, which I think is a much better example? Because we're getting into weird examples with the magnesium chloride, because what kind of bond do we have there? What bond is between magnesium and chlorine? It's a metal and a nonmetal, which is known as an ionic bond. When we're looking at Lewis structures, we're looking at an actual sharing of electrons. So magnesium chloride is a pretty awful example as far as that goes. To get 2 groups of electrons with nonmetals, I needed to do a different structure that we'll come back to in a little bit, actually. But it's going to require multiple bonds. Okay, so the magnesium chloride, not the best example for this, but it does get those 2 directions. Okay? If we move to BH3, okay, this is going to get back to your same question that you had with the magnesium. We didn't have that octet. How many electrons does boron bring in? 3. Hydrogen? 1. There's 3 of them, so we need to put how many electrons in? Our Lewis structure is this. Do we have an octet on our hydrogens? We have its octet, but we don't have 8 electrons on it. How about boron? Okay. Almost everybody tends to freak out at boron and say it doesn't have 8 electrons, it must be wrong. Okay. We put in all of the electrons we could possibly put in. We are now done with boron. This is the correct Lewis structure. This means boron's chemistry is different than, say, our other elements. But it's different just as much as hydrogen is different. Hydrogen can only have that 1 bond. How many bonds is boron happy with? Just 3. Okay? Can we make boron have more than 3 bonds? Okay. Okay, I like that idea. Let's bring in this species. Okay, and now instead of bringing in a hydrogen atom, I'm bringing in technically hydride because it has an extra electron. Boron can get to 8 electrons, and it can form that new bond with that hydrogen, or that hydride. What kind of bond did we just make? So you're going through shapes. Ionic is the right trend, but it's not ionic because it's still 2 nonmetals. Hydrogen bonding is not a bond. This is still officially a bond. What other bond types do we have? Polar covalent and covalent. We can actually push a little bit more. It's one of those weird gray areas. It's still kind of nonpolar, but it's different from our nonpolar covalents. When we make our nonpolar or even our polar covalents, we had a sharing of electrons. Each atom brought in an electron to share. We didn't get that here. Boron didn't have any electrons. Hydrogen had to bring in 2 electrons to make this bond. It is a coordinate covalent bond. Okay? So boron is the classic example for a coordinate covalent bond. Kind of neat. It also explains a lot of its crazy chemistry when you get into organic chemistry. It's going back to, heaven forbid, the Lewis structure. Because that Lewis structure can now start to explain some of its chemistry. There's another atom that has very similar properties as boron. What atom is that? See, it's starting to mouth it.
Aluminum?
Aluminum. Aluminum does the exact same thing. Why would aluminum do the exact same thing? Same column, same chemistry. Okay? So, if we go back to our BH3, get rid of that silly coordinate covalent bond, how many groups of electrons do we have? We've got 3 groups of electrons. I know I shifted up a little bit. The geometry that we end up pulling out of that is trigonal planar. Okay? Just because the last class left them, maybe. Let's give this a shot, see if I can do it. If we look at a balloon as an electron cloud, so that's our bond, right, between the atoms. That's linear. There's nothing we can do about it. We still have those atoms directly across from each other. If we make 2 electron clouds, those electron clouds get as far away from each other as possible. What shape do we end up aligning? Again, linear. If we brought this closer, now that other one goes, oh, you're too close, and chases away the other direction. So we get linear. What happens when we bring... Thank you. When we bring in the other one, without my hand getting in the way. They're going to get this triangular shape, but they're also going to want to fit into a plane. So they're all effectively 180 degrees away from each other. So we get trigonal planar. What happens if we bring in yet another group? Now are they all in the same plane? No. Now we're in a tetrahedral structure. Okay? So that's effectively what someone did to go through and predict these shapes. As they started to say, look at these space-filling things repelling each other. What shapes do we generate? Okay? So this is our electron geometry. We can go through and do this all the way down. Okay, so we get 6 different geometrical shapes that come out of it. Where do the geometrical names come from? Somebody made them up. That's it. Okay? They looked at linear and they said that's most likely to be linear. Most people would look at that and say it's a linear shape. Same thing with trigonal planar or tetrahedral. We tried to pick names that most accurately reflected that shape. Okay? And sorry, my pictures ended up coming in skewed. So if we went through and looked at our pictures, that first linear represents our magnesium chloride, trigonal planar, tetrahedral. Okay? So because I copied and pasted this image from another file, okay, our HF would be not drawn on here, but we can draw it in real quickly. There's our HF molecule. Okay, and we get that linear shape. Okay? The drawings are supposed to help you visualize. You don't need to be able to draw these, you just need to be able to see them so you can work with them. So now we move into molecular geometry. Okay? And if we looked at the Lewis structure for NH3, we'd notice that we'd probably get something similar to CH3. CH3 has 4 groups of electrons. How many groups, or sorry, CH4 has 4 groups of electrons. How many groups of electrons around our NH3?
3. 4 groups.
4 groups again. The 3 bonds and a lone pair of electrons. So we would predict the same electron geometry, the same relative shape. Okay? Because those electrons are going to push away from each other. Okay? When we looked at electron geometry, though, we assumed that all of the electrons are the same. Okay? So in CH4, absolutely. We get 4 bonds, all of them to hydrogen. They're all exactly the same. NH3, are all of the electrons exactly the same? I know. What's the issue? Something a little bit different. We've got a bonding pair of electrons versus a non-bonding pair of electrons. How does that change where the electrons are located? Okay, what we ended with last week, I take 2 electrons. If I'm going to hold on to them, they're right next to me. But if I'm now going to start to share those electrons, what happens? Go ahead. Sorry, I was just messing with you. What happens to the electrons? They start to get away from me. Which means, what about the amount of volume that they're occupying closest to the atom? More or less volume? Less volume when we make a bond. More volume when they're a non-bonding pair. How does that change our shape? Well, if my hand, with my wrist being one of the atoms and my center knuckle in the middle there being the nitrogen, okay, if we looked at NH4 or CH4, we'd have our general tetrahedral shape, right? Nothing's in directly a plane. If we now make it NH3, that top bond, those electrons now come closer to our nitrogen. What is that going to do to the other bonds? Okay. This takes a little bit of visualization to deal with, and I know my hand isn't the greatest, but model kits don't work very well either. We take our electrons, all nice and equally spaced, and now I bring these electrons closer to the atom. What happens to these electrons?
Push them out further.
Okay, if I bring the electrons and I push them out farther, what happens?
Oh, they spread out.
They spread out and they get closer or further to the electron source. They get closer. We're taking my knuckle, my finger there. If I bring the electrons down and those spread out, the electrons get closer to the lone pair. Does that make sense? Should I take the electrons in a bond and bring them closer to electrons not in a bond? What happens when you bring electrons near each other? They repel. So if I bring the electrons down, where do my fingers want to go? Away from it. Because these electrons get pulled closer. We're trying to get those electrons as far away as possible. So what ends up happening is, instead of having a nice tetrahedral structure, it shrinks a little bit. Well, that slight shrink now changes the structure. It's now no longer tetrahedral, missing that part of the atom. Okay, so what happens? Well, we have to give it a new name. What new name do we give it? Trigonal pyramidal. Okay, or pyramidal, depending on how you were trained. Okay? So what we're looking at is evaluating the groups of electrons around our central atom. Are they all the same? Then we get the exact same molecular shape as we get the electron geometry. But if they're different, if we have non-bonding pairs of electrons versus bonding pairs, we end up getting different shapes. Okay? Because they are now shaped differently, they get named slightly differently as well. You'll notice with the trigonal bipyramidal and the octahedral structures, our groups of 5 and 6, we get even more names coming off of those. So this picture is trying to show as best as it can what happens to the overall shape. And remember, your molecular geometry, we're looking at the atoms. We tend to ignore the electrons. Okay? So again, someone went through and just decided on a name, on what best represented that. So those are the names that you're typically responsible for. What I would expect you to absolutely know inside and out: linear, trigonal planar, and tetrahedral. You should be able to give me those 3 without a moment's hesitation. The bent, trigonal pyramidal, and the other bent, we're kind of in a gray area on that right now. I don't want to make you memorize that, but I need to see what the final has, if the final is going to ask you to have those memorized or not. Okay? So until I see that, I can't make that official statement. If you have to take any more chemistry, you might as well start getting those shapes memorized now. Okay? Because all that's going to happen when you move further into chemistry is they're going to make you memorize some more things, like what's the bond angle in a tetrahedral structure versus a trigonal pyramidal. Okay? At this point, you just need to know that the shape is different. So let's look at some tricky molecules. Let's start with our carbonate, because we've already seen that one. Draw out our Lewis structure. Get our dots in there, our line. And one of the things that I'm going to leave off when I draw this is number one, the charge. Why do I not want to draw the charge right now? Because to answer this question, it's completely irrelevant. I want to know the shape around the central atom. So that's our carbon. I don't care that it's negatively 2 charged. All I care about is where the electrons are. So I had to account for those electrons in the structure, but at this point I don't need to see that. All I need to see is what electrons are around that carbon. The other big thing that I left off, is this the correct Lewis structure for carbonate? The brackets give us the charge. What's the other statement? We need the other 2. This is only 1. Why do I not draw the other 2? We're going to get the exact same shape with all 3 structures, so it doesn't matter. Okay, so for the sake of this argument, we can stick with just this one. So now we want to pick our center atom. Hopefully everybody sees the carbon as our center atom. And we now need to evaluate the electron groups around that carbon. How many groups of electrons are around the center atom? Okay, hopefully you see this as a group. Yes? And this is a group. Do we see any non-bonding pairs of electrons?
Yes.
Okay, you said yes. Where do you see the non-bonding pairs?
Well, they're all around the oxygen.
On the oxygens. Do we care about the non-bonding pairs on the oxygen? No. Your shape is dependent on the central atom. The central atom does not have non-bonding pairs. Okay? I was fishing for your answer, so that's good. Okay? So around our central atom, there are no non-bonding pairs of electrons. We do not count any of the electrons out on the oxygens. Now we run into the tricky part. What do we do with that double bond? Is that one group or 2 groups? The big hint. 1 group of electrons. What? Why is it 1 group of electrons? Okay. A group of electrons must be in its own unique space. So when we looked at our single bonds, why did we decide those were 2 groups of electrons? Those are electrons being shared between carbon and a different oxygen. When we look at the double bond, where are those electrons located? They're shared between the exact same atoms. So that is 1 group of electrons. It just happens to be a really big group. Okay? So how many groups of electrons do we get around our carbon? We get 3 groups of electrons, which puts us into what electron geometry? Trigonal planar. We then want to evaluate our structure. Do we have a difference between bonding pairs and non-bonding pairs? Do we have any non-bonding electrons in carbonate? No. They're all bonds. What's our shape? Stays trigonal planar. There is no change to it. Questions on that one?
Does the double bond change the shape of that apple?
Yes and no, but indirectly. The double bond is changing the shape by making sure that we don't have a pair of electrons on that carbon. As soon as you bring in a double or even a triple bond, we can't be tetrahedral anymore, okay, as far as you guys are concerned. Okay. The last example I want to look at before we move on is CO2. How do we start CO2? Carbon has how many valence electrons? 4. Oxygen has how many valence electrons? How many oxygens are there? What's our charge? What's our charge? Neutral. So we could do +0 if we really wanted. What's our total?
16.
Oh, that is 16. Why can't I ever get that right? 16. What's our central atom? Why carbon? It's the least electronegative. Okay, we can then scatter our oxygens around. Why did I scatter them that direction? Trying to get them as far away from each other, and ultimately I know the answer, so I know where they're going to be farthest away from each other. We'll start putting electrons in where? Around the oxygens until when? Do we have full octets?
I thought you started with the central.
So this is, again, a difference in method. The central atom is something that's discussed by the textbook. My opinion, it's awful because you won't find the resonance structures as easily. If you put the electrons on the most electronegative, you can generate your resonance structures much more quickly and efficiently. Okay. What's our next step? Turn into lines. Let's get our bonds in there. Next step.
Well, carbon's not very happy right now.
So it's verifying octets. Our carbon does not have its octet. What do we need to do to fix that? So all sorts of answers were floated out on that one, or really two. I heard move pairs of electrons and double bond. Okay? Both of those are technically correct for this class. Which of them is more correct as far as I'm concerned? Move the electrons. Okay? The motion of the electrons in between that space makes the double bond. The double bond does not force the electrons in. Okay? Very subtle difference in that, important for future chemistry classes. So we could move it in from the left-hand side, that's right-hand side, and we'd have a double bond. Is our octet satisfied on carbon? No. What do we have to do?
Move the other side as well.
Why do we move the other side and not with the original, or right carbon?
Symmetry.
Stick with symmetry. Okay? We now have our Lewis structure for CO2. What is the shape or the molecular geometry for this molecule?
Linear.
You're going, dang, you just jumped straight ahead. Okay, pick our center atom. Carbon, what's our groups of electrons? 1, 2 around the carbon. We're looking at linear. Okay, this is the best example for two groups of electrons. Okay, not that magnesium chloride. The reason I do magnesium chloride is this one brought in double bonds. I didn't want to see that yet. Okay, kind of get the idea? Questions on this? How many of you can draw these shapes? Really?
Been doing it.
Do you need to draw these shapes? No, you do not need to draw the shapes. You need to be able to tell me the names of the shapes. You do not need to be able to draw them. Okay? If you can draw them, good for you. That's actually kind of cool. Okay? Last slide as far as this chapter goes is a shape summary. So this goes through and evaluates all of the possible electron groups, what your electron geometry would be, and then looks at the possible bonding versus non-bonding groups, and then looks at the molecular shape based on that comparison. Okay? This one is a little bit more full than that last diagram. The only thing that's an issue with this is we don't have the pretty pictures. But it gives you all the names, all the shapes, all that fun stuff that you would need. Okay? So if you have 4 groups of electrons, you would immediately jump to the tetrahedral shape at the bottom. What can you tell me about everything else on that table? It is completely useless. If you tell me there's 4 groups of electrons, do not look at trigonal planar. Do not look at any of those other linear options because those do not apply to that electron geometry. Okay? Once you're now in the tetrahedral electron geometry, you can start to evaluate. Do you have 4 bonding groups of electrons? Well, we can't possibly have any non-bonding. The shape stays the same, tetrahedral. What happens if we go to 3 bonds, 1 non-bonding? Shape is trigonal pyramidal. Oh, I thought I did that wrong. Okay. What if we have 2 bonds, 2 non-bonds? Bent. Okay. All of the shape information is included within this. What you would need to do is that initial assessment. How many groups of electrons there are around that individual atom. Where it's tricky, remember, your double bonds can actually be counted as only 1 group of electrons. We have to be in a unique space. Okay. Questions about any of that?
This is going to sound really dumb, but I have to ask it.
Yep.
Electron group, I mean, I probably know it. I know it when you tell me what it is, but tell me again, electron group, as it relates to this chart.
So trying to go through and tell you what an electron group is very, very difficult to do. Okay? It is a group of electrons, so 2 or more electrons located between atoms.
Okay.
Or between, we can't even say between atoms, it's between space.
It's the two dots or it's the line. Okay.
Does it have to be a single line?
No.
No. Okay. If we did,
If you have
Yeah,
two,
that works.
if you have two lines, then you have two.
how many electron groups do we have around the nitrogen?
Two.
Anybody want to volunteer? Step out on the limb?
Oh, yeah. Four, actually. Yeah.
3.
3.
The double bond does not count because the double bond is 4 electrons located in the same space,
Okay.
one group.
Okay.
Okay, so that's why I was saying you've got to be careful on those definitions. I don't think I can give you a strict definition
No,
of
that
it.
answered it. That answered the question.
Okay. That puts us at the quiz, or unless there was another question. Okay. That puts us at the quiz, which is somewhere. We're going to have a quiz every time. Yeah.
Are you going to raise the percentage that it's equivalent to?
All I'll end up doing is giving you the higher score. So if we take 100 quizzes, and half of those quizzes you miss, or if I grade half of them, then hey, we're gonna have a quiz.
And so the quizzes are gonna be on what? On what we covered last time, or what we covered this?
So if we take a look at what this quiz has on it, it's got material that we covered last week, this week, and it's covering material that is yet to be talked about,
Okay.
Do you want us to
which needs to be closed note in this case. Right, what?
Do you want us to write the problem for?
I don't need the problem, just give me 1, 2, 3. Everybody get paper? Okay, and we are going to make this fast. We'll give 4 minutes. As soon as you get it done, you can hold it up and I'll come around and grab it. Good. So we're moving into Chapter 7. All of the Chapter 7 and Chapter 17 slides are now in this slideshow. Something like 40 slides. Okay? So I'm not going to post new slides for Thursday. I will probably have new slides posted for Monday that I'll just go ahead and label, hopefully as Chapter 8 and Chapter 9, but it might just be Chapter 8, kind of see what happens. All of the homework is posted to Canvas. Because I believe your section asked for it first, so hurrah, good job. One of the other things that I forgot to note, at least initially with that posting, is I also attached to be completed by dates, because several people have asked for that. The intent on the to be completed by is not turn it into me at that time, because I don't want it then. I want it on the day of the exam. That is when it is due. But you should have it completed by the time we finish talking about that material. Okay? So I think I added maybe a few days extra after the completed by date, or when I expected to be done with that lecture, hopefully. Because we are running a little slow, we might see some shifts with that. Okay? But that is kind of the intent, is to get you doing the homework ahead of lecture, so when we talk about it, it's a little bit easier to get through. Okay? I will try and be more specific with those dates in the future as well. Chapter 7 ends up reviewing chemical and physical changes. I'm not particularly happy about that because we started off the semester with looking at chemical and physical changes and came across all sorts of weird definitions and when was it chemical, when was it physical. And ultimately, we hadn't discussed atoms or molecules, so how can we describe what's happening in a chemical or physical change when we don't even know what a chemical is to be able to describe if it's changed. Okay? So we're now reintroducing the topic to kind of hopefully broaden that definition a little bit. Our physical change is looking at a change that does not change the chemical composition. Okay, so now that we've got some idea of what makes molecules, we're going to push this further in this chapter. What we're looking at is that that composition does not change. It stays exactly the same. But we could change the phase, for instance. Our chemical change means we change the chemical composition. Okay? We're looking at a chemical reaction occurring. Well, that is very difficult that we didn't know what a molecule was. Now we got a better idea of a molecule. Let's look at a couple options for physical versus chemical changes. Let's try ice melting. Physical or chemical? Physical. We're taking molecules that were nicely stacked next to each other, and then those molecules now start to move more. So it's a physical change. How about, let's do sugar dissolving in water. Physical change. The sugar stays a sugar molecule as it dissolves in water. It's a tricky one. Okay? The whole dissolving process is, in my opinion, very, very tricky, and we're going to see that with the next one. So sugar in water, say, is physical. All we've done is taken individual sugar molecules and now separated them by water. Okay, so it's still sugar. Salt dissolving in water. We now have an interesting question with this. Most people, at least when we first started talking about it, we kind of look at how easy is it to reverse. An easily reversible reaction we look at, it's calling physical. And a chemical one isn't reversible. It's not the best definition. What happens when we dissolve salt into water? And this is, again, a stretch because we haven't quite covered that information of what's happening in that dissolution process. We take molecules of sodium chloride that have ionic bonds. We break the ionic bonds to now have a solution of sodium ions and chloride ions. Do we have sodium chloride anymore? We've changed the bonding characteristic. So now the dissolving of a species, instead of being physical, could actually start to be classified as chemical. Okay? That line is a very difficult line to walk and interpret. So when you're dealing with these physical and chemical changes, first off, we'll ask questions that don't walk that line. Like we won't ask salt dissolving in water, okay? Because that is an awful question as far as which one should it classify as, particularly with your knowledge. If we asked someone in biochemistry that, we would expect them to know, okay? But we don't expect you to know that yet. That said, the final is not written by me. I have no idea what questions they put on it. And if we do see that question on the final exam, any ideas what's going to happen? Officially, nothing. I will not tell you anything about what happens, but what I will do is remove the question from the exam. The reason why I won't tell you is undoubtedly you will tell somebody else. That somebody else tells somebody else. But it eventually makes it back to another instructor, and then I get yelled at for it. So I'll just fix it and not tell you. Okay? So I will look out for you in that respect when it comes to questions that I just don't think were fair or poorly worded. Okay? Doesn't mean it always works in your favor, but sometimes it will. Okay? So remember the definitions, try and keep them separate. One extra thing we're going to do to help facilitate this is actually look at evidence for what makes a chemical change. And we would assume anything outside of these limits is now, sorry, I lost my train of thought, a physical change. So the textbook specifies that we get 4 observations. I make the argument that observations 1 and 2 are the same thing, so I've grouped them as one section. We look at a change of phase. Interesting. What happens when ice melts? Is that a change of phase? Solid to liquid? Is that a change in phase? Yes, that is absolutely a change in phase. Why is that a physical change, whereas the change in phases I'm talking about here are chemical? When we look at the physical change, we are supplying the energy also to cause that change. When we're looking at a chemical change in phase, we do not supply or remove the energy. Okay? It has to be something supplied by the reaction itself. Okay? Not the easiest thing to see, but in an experiment, if we took 2 clear solutions and we mixed them and saw gas, did you add any energy? No, what happens if we took two clear solutions and we put them on a pot of boiling or on a hot plate? We added energy. Okay, so it is something that we can see and control in the lab. So the two big phase changes the textbook makes reference to, gas forming and solid forming. Those are your two big ones. Okay? For a gas forming, you can see a light fizzing to heavy bubbling. You have seen this already when you reacted carbonate or baking soda, I think. Baking soda with your vinegar, you should have seen some bubbling. The picture here is supposed to describe that or show that. Okay? The solid forming. This case is probably one of the more dramatic ones. It's probably lead iodide, I think, which forms a nice deep yellow solid. So we mix two clear solutions, and in the process of mixing those, we see a solid form. That is now a chemical change. We did not remove energy on our own. All we did was mix the reactions and let them do their thing. Okay? What we then have is a chemical change with the formation of that solid. Because formation of solid is way too many words and letters, we strung it all together to make it look fancier and called it a precipitate. Okay? Next one's another fun one. Permanent color change. Okay, we got to be a little bit careful with this one. If I take red food coloring and blue food coloring and I mix them, what do you see? Purple. Is that a chemical or a physical change? That's a physical change, not a chemical. Okay, what's the difference? Again, what's happening in it? That's a mixing of two colors. We didn't actually do a chemical reaction. We just saw the blending of two colors. Okay? So we have to be careful with the color changes that it's not a dilution. Okay? You're looking at a formation of a brand new color that we couldn't see from the combination of the pieces that went into it. Okay? Last one, an energy release or an energy change, not energy release. So if we see an energy change, then we have a chemical reaction. Okay? How do we see energy changes? Okay, there's two primary ways to see it. The biggest one is heat. Okay? How do we see heat change? Temperature. We would measure the temperature of the reaction. If the temperature got hotter, what happened? The reaction had to give up that heat so that we could feel it as heat. Okay? That means the reaction released heat. That is known as an exothermic reaction. We gave that a negative sign. Okay, what does that negative sign mean? It means loss of heat, but it means energy was a product. Okay, we'll see in a couple slides what we can do with that sign. If it absorbed heat, what did we feel? It should feel colder. It's taking heat out of our hands or out of our measuring devices. Okay? That is an endothermic reaction, and that is positive. The other big form of energy change that you can see or measure would be a light emission. Okay? Is light actually a form of energy? Yeah, it is. Okay? We're looking at the electromagnetic spectrum. Light is an energy emission. So if we see, it's usually going to be an emission of light. For instance, if we threw sodium or something like that into water, we usually see light formed as well. Okay? Think about combustion. What happens when you combust something? You see a flame. That flame is light energy as well as heat in some cases. Okay? So those are going to be your four primary categories for chemical reactions. Questions about any of those? Okay. Cool. I think we'll get to the exact same spot. What information does this following equation provide? So piece it out. Feel free to give me something.
Tells you what forms. You've got gas, liquid,
Okay.
solid.
Okay, now you got to slow down. What was the gas? A, how do you know that's a gas?
It's got a little G beside
The
it.
G beside it means gas. What was the next one you told me?
Liquid,
How do you know it's a liquid?
L beside it. There's a B, and then the C is a solid. So that brings me to a question though. And then the D is aqueous, which is liquid.
Be careful with, and Okay, so AQ absolutely means aqueous.
Yes.
Oh man, I can't abbreviate. AQUEOUS?
Yes.
Thank you. Okay. So I want to first address what you were saying because that was probably picked up. You said that means a liquid.
Yes.
Does aqueous mean it's liquid? No. A liquid is when that single species is not a solid or a gas. Aqueous does not mean that D is a liquid. What aqueous means is that D is, for those of you saying acid, what does that D mean? Don't tell me it's acid. Aqueous means D is dissolved in water. That's all it means. Okay? Which brings us back to the acid statement. If we knew it was an acid, what was our big tip-off when we did nomenclature? AQ is what everybody said D was an acid. What else do you need to be an acid?
Hydrogen.
You have to have hydrogen. Does D say anything about hydrogen? No, we cannot say D is an acid. Okay? It has the potential to be an acid, but it is not defined as one yet because we don't have that hydrogen. Until we have that hydrogen, it is not an acid.
So what is it? It's a dissolved
So
water.
AQ means that that species is dissolved in water. Why do we add that as an extra thing? Actually, we'll come back to that. We'll come back to that in a second here. Does our reaction tell us anything else? Okay, so I heard those two combined, so I believe what you are referencing. Oh, we'll just do this. What does that plus symbol mean? Reacts with really only works in a certain circumstance. Really, our plus sign just means combined. Okay? So our plus symbol gives us some information. We have these things now in the same area. What do you mean reacts with? Which plus symbol means reacts with? I know. Doesn't mean the book's right. What do you mean left? What does the left side of that arrow mean?
Those are the reactants.
We have reactants and we have products. How do we know one side's reactants, one side's products? It's all based around our arrow. Okay, so our arrow is our reaction. Okay? We took A and B, we mixed them, they then reacted to produce, C and D. Okay? So our basic equation gives us a fairly sizable amount of information stacked up into that. Okay? As far as what you guys need to specify, how much of this information do you need to write out? Okay, you don't need to tell me what all those individual pieces are. You don't need to give me all the colored stuff in there or even the combined thing. If I asked you to write out a balanced equation, you're going to have to tell me what your reactants are. You'll separate them with the plus sign because otherwise you're saying they're connected. If we get rid of that plus sign, A and B are now one unit. Okay, so that plus sign is our way to separate the individual reactants away from each other. Okay? We do the same thing with our products. So we need minimally our individual reactants separated by our plus sign, then our arrow so that we now know we're shifting to our products, and now our products separated by that plus sign. Bare minimum. Thankfully in organic chemistry that's all we got to worry about, but you're not in organic chemistry yet, so what's the problem? What else do you get to specify? You get to specify all of the phases as well. Okay? So if it's aqueous, you have to specify aqueous. If it's a solid, you have to specify it's solid by using that notation, your parentheses and then that phase symbol. Okay? At this point, you might go, oh, that's not that bad. Give it some time. Okay? Questions about any of that formatting? Okay. Your textbook goes through, broke those down into a table so we could see individual systems with each of those. couple things I want to address. Number one, I want to go back to the AQ. Why do we separate, or separate? Yeah, why do we separate AQ out as its own phase?
Well, I would think that it'd be because a liquid is, is just a liquid, whereas an aqueous could be something that was created by taking a solid or whatever, and water, mixing the two, and then you get an aqueous solution, whereas a liquid stands alone by itself.
So yes, the liquid stands by itself, agree, and your aqueous, you brought up the good point too. The aqueous comes in with water. As soon as we specified aqueous, we now know water is in that reaction. Well, why didn't we just write water in the reaction to begin with?
Because that would be inaccurate. Water is H2O, whereas that could be something else.
AQ always means water, always means H2O. When we write out our balanced equation, the things that we put in are our reactants and our products. Water is not a reactant or a product. It's there as the solvent, as the solution. So what we want to do is necessarily imply that there is water present in the reaction, but that it's not a reactant and it's not a product. So we're adding an extra layer of information without convoluting our reaction even more. Okay, so that's why aqueous is added as an extra phase. Next two things that I want to look at, let me check real quickly. Oh, shoot. We're going to have to cover that too. We've got this guy right here, this guy right here. What is the symbol above the arrow, now circled in red? Delta. What does delta mean?
Change.
Change. What is changing in this case? The temperature. We are changing the temperature. And in all cases that you see a delta, that means we are increasing the temperature. What does that mean? In the course of that reaction, we added heat. Okay, so that's what that delta symbol means. What?
Is there a way to take away heat? Way to show that?
You wouldn't show that per se. You'd specify a temperature range. You could say it was run at 0 degrees Celsius. What is the symbol above the next arrow? Fe or iron. Why is that there?
Showing a catalyst.
What is a catalyst?
Something that speeds up the reaction, but it doesn't, it's not part of the reaction.
So in the morning, someone actually read me the definition, which was fun. The catalyst is something that changes the speed of the reaction, so it makes it go faster. Okay? But it's also something that is not consumed in the course of the reaction, and it's not produced. So if it's not consumed or produced, it doesn't really make sense to put it in the reaction itself, either on the reactant side or the product side. We could put it on both sides, but then we just wrote the same thing twice. So someone went along and said, I bet you there's a lazy way to do this. Let's just put it over the arrow. Now we can call it a catalyst. Okay? And that is effectively what they did. So as far as you're concerned, if you see a symbol above the arrow, an elemental symbol above an arrow, we're using that as a catalyst. Okay? Last thing that I want to look at, I promise. Yep, I promise. Chemical reactions. If we take this chemical reaction, one of the things you're going to be responsible for is converting both the equation into words and words into an equation. So if we go through and read that first equation, I'd start off with solid sodium hydride. What? How did I know that? S is solid. How did I know NaH is sodium hydride? Because I did a really good job at all of my nomenclature in chapter 6. Okay? Yep. Okay? So solid sodium hydride is mixed with or is reacted with, right idea, you got the acetate ion, but it's aqueous and has a hydrogen, so we're looking at an acid. We take solid sodium hydride, it is reacted with acetic acid to produce, there's my little arrow, sodium acetate, or aqueous sodium acetate, and hydrogen gas. Why does it say H2, not just H? Some elements are diatomic. In their elemental state, you must specify them partnered. So when we refer to hydrogen gas, it is H2. It must be written as H2. How do you know that? You're lucky. You get to memorize it. Okay? A couple memorization techniques. We've got the list there: hydrogen, nitrogen, oxygen, halogen, fluorine, chlorine, bromine, and iodine. Okay? There are 7 of them. So a couple ways that I could go through and suggest this. We have hydrogen plus 7. See the little 7, right? There we got our 7. Foot cramp. Other option is a little phrase at the bottom of that: have no fear of ice cold beer. We got a nice little phrase that goes with that some people apparently remember better.
I'll drink to that.
I can't condone or deny that. We got the H for hydrogen, no, N for nitrogen, etc., all the way through. Okay, to set that up with your diatomic molecules. We will pick up there on Thursday. We're going to look at a lot of balancing of reactions. All right.